Welcome back to my channel. In this video, I will discuss about a very important topic of our steel structure design, right? And what's that? That is, yes, your lateral torsional buckling. If you're new to this channel, you may find these terms are quite difficult, or if you are at the very beginning of your career, in that case also, this lateral torsional buckling may be a difficult topic for you, but trust me, at the end of the video, definitely you will get some insight about this very important topic, right? So what's going to be discussed in this video? At the very first, we'll try to understand what is lateral torsional buckling, right? And then definitely we'll try to understand why this happens, and also what are the different structural factors that can affect our lateral torsional buckling. And at the very end, as an engineer, we will try to solve the issue. Okay, so without wasting time, let's start the video. And if you're new to this channel, please don't forget to subscribe it, right? So let's start. At the very first, what is lateral torsional buckling? There are actually three terms, right? Lateral torsional buckling. Okay, so from this name, it is very clear that there is something going to happen, twist, right? From this name, it is clear. Torsional means it is related to something twisting, and buckling means, if you are familiar with column buckling, yeah, this is similar thing. Here also something will buckle. If this is something straight thing, then buckling means it's going to buckle like this, right? So a straight thing is going to buckle. And finally, the last one, but here as per the name, this is the first term, that is lateral. Okay, so let's try to understand what is lateral torsional buckling is. So in my PPT, there are two things has pop up. First one, compression at top flange, tension at bottom flange. Well, that means if this is I section, our beam, okay, and if this is the loading, this will be the bending moment, right? So at bottom, this is going to carry the tension. At top, this is going to carry the compression, right? So these things are actually prepared by my team, and that is why first I have to take the hints, then I have to discuss it, right? So don't mind, please. So this is the simple thing, right? Compression at the top flange. So what will happen if the top flange of any plate girder or I section or H section or W section, whatever may be the name, doesn't matter. So what will happen if it is under compressive force? Yeah, if something is under compressive force, then it will buckle. But here the compression flange will move sideways. Well, there are a lot of questions here. Why the compression flange buckles? Why it moves sideways? And once it moves sideways, the shape become like this, right? It was initial shape, and once loading has been applied, due to this buckling, it has bent, right? Not in vertical plane, actually it is in horizontal plane. So if we took the plan view, if it was initially shape, now it has become like this. This is the plan view, right? So this phenomena will happen, and it is known as torsional buckling, right? So what is the questions now? There are a lot of questions, right? So if we don't answer all these questions, we do not understand what is lateral torsional buckling is, or why this happens, and also as an engineer, what are the solution we have to provide, right, to prevent this one. Because we don't want that we will design a beam like this, but after application of load it will be shifted. So here you can see the drift. This is the drift, horizontal drift, right? So the plan view looks like this. So of course it is not desirable at all, it's a failure. So let's try to understand why this happens. So at the very first, column buckle about minor axis. Well, it's fine. Let's try to visualize that. If this is the column, if we apply the axial load, definitely it will buckle. Thanks to my team, they have put very beautiful figure. uh, yeah, So it will buckle definitely about the minor axis. So if this is the column plan, so this is the what axis? This is the minor axis and this is the major axis, right? So our beam is placed like this. Here is the load. So this is the major axis, right? This is the minor axis. Okay, great. Compression flange also behaves similarly. Wow, that's the point. So this is actually the point here. Compression at the top flange, and this compressive force actually buckle this flange. That is why it's moved sideways. Right, now we have got the answer. Okay, yeah, now it's clear. Compression flange will definitely, if this is the, yeah, they have put the I section also. So this is tension, this is compressive force. So this compressive force is acting like this. Okay, so if assuming it is fixed, this is also fixed, and we simply cut this out, it is subjected to a compressive force. And of course this compressive force will uh, try to buckle this top flange. But now I have a question, right? Here it was written that the compression flange moves sideways, right? In this figure also it is clearly shown that it has buckled in sideways. Why not in vertical direction, right? That is the question. So wow, so why, this is my question, right? Why sideways, not vertically? That is my question also. It is clear that here compression flange has been, the top flange has been subjected to compressive force, and the compressive force always try to buckle the member about its minor axis. Then why sideways, not vertically? Well, we have already got the answer. Column will always buckle about the minor axis. Now, if this is the beam, this is the major axis. So to buckle vertically, it has to buckle about major axis, but it is not possible, right? Always buckling will occurs about the minor axis. So if it has to buckle about minor axis, then yeah, it will buckle sideways. Why? Because Iyy always less than Ixx. Simple physics. So now it is very clear to us why buckling happens, where buckling happens. Okay, so it's enough. That is lateral torsional buckling. It's time to get out the solutions, right? Okay, so if we want to find out the solutions, if we want to cure the disease, what we have to do first, we have to first find out what are the viruses. Only based on that we can put the medicines, right? So here, what are the factors? So one thing, it is clear that buckling is related to something, this moment of inertia. That is why it will buckle sideways, not vertically. Okay, so yeah, as expected, the moment of inertia is the very first criteria. Okay, so if the moment of inertia about this minor axis is higher, let's say somehow we have managed to design a section where the minor axis moment of inertia is higher than this one, then what will happen? It will buckle sideways? Definitely not. And if something is not buckling about if something is not buckling horizontally, then it is not lateral torsional buckling, because lateral by default means it has to buckle sideways, right? So what are the solutions? Okay, we will increase the moment of inertia about the minor axis. How that is possible? So this was the initial section. Now somehow if we convert this one like this and eliminate this one. So basically we have converted an I section into a box section like this. Okay, so definitely the moment of inertia about the minor axis and major axis is more or less same, or if we placed these two vertical wave far away, then we will be able to create this situation and our lateral torsional buckling will be eliminated in this case compared to this one. I have already made a video regarding the benefits of these two. That is why I section versus box section. Okay, fine. This is one solution. Next, what are the other factors? Unsupported length. Yeah, buckling means something like to I just would mention here in case of column. Can you remember this ratio? What is this? Slenderness ratio. Yeah. So buckling increased, effect or tendency increased if KL increase or effective length increased. So what if we reduce the length of unsupported flange? Well, try to visualize this. So yeah, this was the beam, this is the compression flanges, right? So here you can see we have connected them through intermediate bracings like this, and by doing so we have reduced the effective length. So initially this was the complete length, but now through bracing action we have reduced it. If you want to know more about the bracing effect, definitely you can go to the playlist. There are lots of videos related to this bracings, right? So by putting bracings we will arrest, let me clear this one. So here you can see by putting bracing we have arrested the top flange. So now if it try to move this way, this is the bracing who will carry the axial load and will resist it, this one. Same way this movement of this top flange will be resisted by this one, right? So by this is the method we can reduce the effective length and we can simply arrest the or eliminate the lateral torsional buckling. Another one is to reduce the length. What we can do, we can simply eliminate the top flange, right? How this is possible? Yeah, this is not possible to eliminate the top flange, but definitely what we can do, we can create a composite section like this one. Here you can see this top flange is embedded within the concrete. So once this is embedded within the concrete floor, what will happen if it tries to buckle this side or this side? Here is the big man, that is the concrete floor. It will not allow it to move sideways, and if we are able to successfully stop the movement, sideways movement, right? So our mission is stop the sideway movement. If we can stop this, we have eliminated LTB. So this is the all about LTB. I am not going into the detail equations in any code, whether it is AISC, IS code. There are all the formulas, but what I have tried to do, I have tried to make you visualize what actually lateral torsional buckling is. That is what I have tried, right? So till now, if you love this video, don't forget to share it, and also don't forget to give a like.